An important aspect when we are predicting products in radical reaction is knowing that the geometry of the radical themselves. So radicals are trigonoplanar, and this is similar to what you had probably studied before about the geometry or cations. So I'm going to draw a radical in the plane that is, say, perpendicular to the screen. So say that I have 3 metals here. In the case of the radicals, let's choose C3 to have a tertiary, right? Because we know it's more stable. And then in the plane of the screen, we will have the p orbital that is, will have 1 electron only. But the electron is not there localized, it's delocalized, it's moving in this region. Say, this is only indicating the probability of finding that electron. So we have that this is, the radical is on the plane perpendicular to the screen, and then this plane we will have that. What this means is that we can have another radical, such as this, coming from one side of the plane or the other side of the plane. And I need to draw fish hook arrows, because these are radical reactions. So if it did this, then we will have one product if different, if the three constituents were different. So that's the case when we are creating chiral centers. This is not the case here because in this radical we have 3 metal, it's a tertiary, but it's 3 metals. So we're not making a chiral center. But where the attack is happening matters when we are creating a chiral center, or if we already have one chiral center. So we're gonna analyze this molecule now. Let's first say how many predicts how many products. So I'm gonna label positions here. If this position here, A, is primary, we're gonna make primary radicals. This position here is also primary, but it's different. That's another product. Position here, let's call it C, that's secondary radical. Position D is tertiary, but notice that D here is a chiral center. We know that because here you have at the carbon here, and let's make it, I'm gonna make like a little square here. This center is chiral because you have methyl, ethyl, and isopropyl plus a hydrogen that is not drawn, and they would be on a dash. So that's a chiral center. And yet we have more positions here. We will have this is different. Notice D is tertiary and is different to this product. So here you have another tertiary position. And now we have these two will be equivalent, so I'm gonna say F. So overall, notice how many products that we have, different products. So, but we were talking about why is important the geometry. So you can do the exercise of drawing all the products that will result, following this, that will result by replacing one of the hydrogens with, say, chlorine. Let's say that we're making this react with chlorine. So draw in monochlorinated products. Mono means you're replacing only one hydrogen. We're doing monochlorination. And we will have all these possible products. So notice now, let's talk about the center. It is not a chiral center. And if you think, if you're making a radical here, and we can draw it similar to what we had on the board, on that side, we will have 2 metals, and we will have 1 bond, and I'm gonna call all of these R. That's here. But if I am making that radical, regardless on if I have a chlorine attacking on this side, or if it does the attack on the other side, you're not gonna get a chiral center because you have 2 metals. That's our point here. However, if the attacks, instead of happening in E happens in D, let's see. Now I'm gonna do a different situation. Let's change. I'm gonna change this with the substituents that we have. Well, no, I'm gonna make a different drawing, change my mind. Okay, let's do that. And here I am abstracting the hydrogen D. But notice when I remove the hydrogen D, I no longer have this structure here. The geometry about the center D is tetrahedral, but now this becomes trigonoplanar. And if I do, well, let's do that. Same strategy I did before, say that this is carbon B. And now I will have an ethyl, a methyl, and I will have another group that is this. So now this has a specific configuration to it. So in here you see the highest priority is the isopropyl. Then you will have the ethyl, then the methyl. The hydrogen is in the back, so this is actually R. But once you have this and you remove the hydrogen at the center, you have that. That's no longer chiral, so it is trigonoplanar, and you can have the attack of chlorine either one side or the other side of the plane. That leads to the formation of two products, which are enantiomers to each other. So at the end of the day, the two products that are formed from the attack at D are two enantiomers and formed essentially at the same amount. So that mix of enantiomers is called a racemic mix. So overall, we said that we have 6 products, counting all of those different positions, but the attack without the stereochemistry, stereo, we have products A through F. That's 6 products, but taking into account that at this position you're creating a chiral center, then it's one more product. So with stereochemistry, then you have one more products. So you will have the 6, but these is replacing D is 2 products. So one more. Okay, we're gonna be using that. So keep in mind that the geometry of the radicals is trigonoplanar, and we're gonna be looking at the same effects like we did in this example when we are predicting products.